If you throw a rock in deep space, Newton's first law suggests it should continue with constant velocity in a straight line, forever. However, in our expanding universe, something else happens. It eventually slows down and stops. This presents a profound paradox. Where does the energy go? The law of conservation of energy is a bedrock of physics. If the rock's kinetic energy disappears, it must go somewhere. This question puzzled great minds, including Albert Einstein, who faced a similar problem with his new theory of gravity. In Göttingen, 1915, Einstein was finalizing his general theory of relativity. A major hurdle was that the theory didn't inherently account for the conservation of total energy. Mathematician David Hilbert struggled with the problem, finding only the Bianchi identities, which showed energy was conserved in a completely empty universe. Einstein's proposed solution had a fatal flaw. His equation for gravitational energy used a pseudotensor, which is dependent on the coordinate system. This meant that the laws of physics, a core principle of general relativity, were not independent of your frame of reference. Hilbert knew the right person for the job, his new assistant, Emmy Noether. She was a mathematical prodigy who faced intense institutional sexism, even being refused admission to her university. Despite this, she became only the second woman in Germany to earn a PhD in mathematics, viewing the problem as a fundamental question. Noether asked a more fundamental question: where do conservation laws come from? Her expertise was in symmetry. Any action you can take that leaves an object unchanged. She realized conservation laws were deep consequences of the symmetries of the universe itself. Her insight led to Noether's first theorem. She proved a profound connection. For every continuous symmetry in the laws of physics, there is a corresponding conserved quantity. This was the mathematical proof of the origin of all conservation laws. The symmetries of the universe dictate the laws of nature. Translational symmetry, where laws are the same everywhere, leads to conserved momentum. Rotational symmetry, where laws are the same in any orientation, leads to conserved angular momentum. And time translation symmetry, where laws don't change over time, leads to conserved energy. This leads to a startling conclusion. Is energy truly conserved in our universe? Noether's theorem states that energy is conserved if the laws of physics are symmetric in time. But our universe is expanding and accelerating, breaking time's symmetry on a cosmic scale. The mystery of the rock is solved. No time symmetry means no absolute conservation of energy. The energy from the slowing rock doesn't go anywhere. It simply dissipates as the fabric of spacetime itself stretches. The energy disappears because the symmetry required for that law to hold is absent. Noether also solved Einstein's original problem. While the universe lacks global symmetries, general relativity has powerful local symmetries. Noether's second theorem shows these don't lead to simple conservation laws, but to continuity equations. This means energy is conserved within any small local patch of spacetime, but it can, quote, leak in or out of the curvature when moving between patches. This was the only solution possible. Her theorems created a new paradigm for physics. Thinking in terms of symmetries led to some of the biggest discoveries of the 20th century, including the conservation of electric charge, the Higgs boson, and the entire language of modern particle physics. Her dedication to mathematics was absolute. In 1933, the Nazis banned Jewish people from working at universities, and Noether was suspended. Undeterred, she continued teaching from her home. She cared only for the subject, not the uniform. With help from other academics, she escaped to the US and taught until her death. Albert Einstein, in her obituary for the New York Times, said, "Fraulein Noether was the most significant creative mathematical genius thus far produced since the higher education of women began." Emmy Noether revealed the language of the universe. By connecting symmetry to conservation, she gave science a completely new tool to understand reality, teaching us a deeper truth about why anything is conserved at all, and revealing the fundamental grammar of our universe.